This video is an example problem where we're going to study the momentum of a system. And our system is these two particles. The particle on the left, so L for left, is 3 kilograms. And at some start of a stopwatch, it has this motion, 5 meters per second, towards the right. On the right-hand side is a particle headed towards the left. It's got a faster speed, 10 meters per second, but it's got less mass. So we'd say that this momentum here is a little bit less. If you calculate it, it's only 10 kilograms meters per second leftward, whereas this momentum is 15 kilograms meters per second headed rightward. A little bit more is these two particles at this starting instant in time are 15 meters apart. Out in the background, an interesting thing is these two particles aren't just going to go in a straight line. They're actually going to fall at the same time. So they're going to go like this, right? So they fall under the influence of gravity. They meet each other somewhere in the middle. They're going to bounce and then fall apart again and go outwards. And I'd like to study the momentum of a system that has an external force. So this is the kind of like the point, is that there is an external force, and I want us to study the momentum of the system. So if you think about it, I've got these 15 meters that separate the initial time, that separate the particles at the initial time. And so if you think of 1 second later, so if I go 1 second later in time, what will happen is in 1 second, this object, it will be falling, right, gaining speed downwards, but at the same time, in the leftward, it's gaining displacement. So in 1 second, it will go 10 meters over, and also in 1 second, this will go 5 meters over. And so, because I get to choose all the numbers in this little playground, I'm going to choose ones that work out nice. So 1 second later is when these two things meet. So I'm going to say, because the left side is the slower side, they meet just 5 meters over from the left side, so like a third of the distance across. And those two objects begin the collision. And for the purposes of this example problem, I'm going to say it's an elastic collision. So elastic is a special kind of collision, where that I described in earlier videos. It's got to do with the fact that there is no energy during the collision, or because of the collision, there's no energy that gets converted away from an overall kinetic energy. I'm probably not being good enough with the language, but that's kind of the point. So this object has fallen down to here. This object has fallen down to here. They have a collision, and they're going to bounce apart and keep going like this, right? And so I want to study this left side ball 2 seconds after the initial time, or 1 second after the collision. And I want to study the right hand side ball as well, but I'm going to end up leaving you to do the work involved here. But you'll see that it parallels very closely the work involved in understanding everything about the left hand side particle. It's going to be moving downwards really fast, but also it turns out in this example, it's headed left as well. The central equation that we're going to leverage is a momentum impulse equation for a system. So the way that goes is the change in the momentum of a system. In this case, we're going to be calculating the change in the momentum of the system from 0 up to 2 seconds. So this will be the system momentum at 2 seconds minus the system momentum at 0 seconds, like this. This is the system momentum. And the change in the system momentum is because of an impulse delivered to the system, so to the system, by external forces. And the external force that we are paying attention to is actually the weight force. So you'll see this come in a little bit. The impulse delivered to the system by external forces you'll remember is an integral in time of the net external force on the system. So, and this in general is a time-dependent function. And for us, because we're doing from 0 to 2 seconds, we are interested in the impulse from 0 to 2 seconds, like this. So we are going to end up having to calculate this, but you'll see that this is actually quite easy. So whenever I want to do anything with a system, and this is true for Newton's second law of motion, and it's true for energy, including the work energy theorem and also the conservation of total energy, and is also true for momentum stuff. The system is sort of the central idea. And in order to describe the system, you have to describe what is so-called internal to the system and what is external to the system. And so internal to the system, I'm going to call them the left side mass and the right side mass. And also internal to the system is the force on the left side mass by the right side mass, and the force on the right side mass by the left side mass. So these things right here, these are internal forces. And the reason is because both of the objects involved in the force are internal to the system. These are my objects that belong to the system. So the forces that are between objects within the system are called internal forces. But here's an external force. It's because of the Earth. So there's an external object called the Earth. The Earth is below these two particles that are having a collision. And what's more is there are external forces involved between the left side object and the right side mass and the Earth. And those external forces are the weight force that acts on the right side object by the Earth, and also the weight force that acts on the left side object by the Earth. So these forces here are external forces. They're external because one of the objects involved is not within the system. I'm only going to study these two objects as the objects of the system, and the Earth is not part of that list. So since the Earth is external to the list, any forces that involve the Earth are considered external. So this force right here, this consideration right here, it's important to note that the other object involved in the external forces, the other object is actually in the system. Yeah. So one object's in the system, one object's out of the system for each of the external forces. For example, we do not include in this external force, it's not important to consider any third or fourth or fifth objects anywhere else in the entire universe. So I don't have anything to do with the moon, for example, in this, or a satellite, or a bird, or a car, or bus, or whatever. Like, it doesn't matter. So this is all I have to worry about in order to finish this problem. Okay, so moving on.